with an insatiable appetite. When we think of a black hole, we often imagine it as a cosmic vacuum, sucking in everything that dares to venture too close, never to be seen again. The idea that once something falls inside, it is dragged inexorably toward a central point called the singularity, where all matter is compressed to an infinite density, is both terrifying and awe-inspiring. But what if we told you that this popular depiction of black holes is not entirely accurate? The reality of black holes is far stranger than fiction could ever conceive. To truly grasp what a black hole is, and what happens beyond the pitch-black curtain of its event horizon, we must dive deep into the world of modern astrophysics, a world where the boundaries of space and time are stretched and where the laws of physics as we know them are pushed to their limits. Black holes are born from the death throes of massive stars, those celestial giants that burn with a ferocity that lights up galaxies. When a star with a mass at least 10 to 20 times greater than our Sun exhausts its nuclear fuel, the delicate balance between gravity and the outward pressure from nuclear fusion is disrupted. Without the force of fusion pushing out, gravity wins the battle, and the star collapses in on itself in a spectacular explosion known as a supernova. The remnants of the star, now devoid of any outward pressure to counteract gravity, continue to collapse until they form a point of infinite density, or so the theory goes. This point, known as a singularity, is where all the mass of the former star is thought to be concentrated, creating a gravitational field so intense that not even light can escape from it. Surrounding this singularity is the event horizon, the point of no return, beyond which nothing, not even light, can escape the gravitational pull of the black hole. To understand black holes, scientists rely on two of the most successful theories in physics, Einstein's general relativity and quantum field theory. General relativity, which describes the gravitational force and the large-scale structure of the universe, works beautifully when applied to massive objects like stars, galaxies, and, of course, black holes. It predicts that as the mass of a star collapses, spacetime around it becomes increasingly warped, eventually creating the event horizon. Quantum field theory, on the other hand, is the framework used to describe the behavior of particles on the smallest scales, down to the level of atoms and subatomic particles. This theory explains the interactions of particles through the exchange of force-carrying particles, like photons for electromagnetism. While quantum field theory excels at describing the microscopic world, it falters when applied to the massive scales and intense gravitational fields of black holes. The problem arises because black holes straddle both worlds. They begin as massive astronomical objects and then collapse to sizes where quantum effects become significant. For example, if our Sun were to become a black hole, it would have to be compressed to a radius of just 1.8 miles, 2.9 kilometers. At these tiny scales, the quantum effects should dominate, but our current theories cannot fully explain what happens in such extreme conditions. The concept of a Schwarzschild radius, named after the German physicist Karl Schwarzschild, helps us understand the size a given object must be compressed to in order to become a black hole. This radius depends on the mass of the object. Larger masses have larger Schwarzschild radii. For instance, the Earth, with a mass much smaller than the Sun, would need to be compressed to a radius of just 0.35 inches, 0.88 centimeters, to become a black hole. But what if the radius of an object were to become zero? This is where traditional physics begins to falter. When calculations lead to an object with zero radius, both the math and the physics break down, leading to the concept of a singularity, an infinitely small point with infinite density. However, such infinities are not something we encounter in the physical world. They suggest that our current theories are incomplete and unable to describe the true nature of black holes. To explore what really happens inside a black hole, let's conduct a thought experiment. Imagine a simple black hole, created from tiny bits of matter floating around in space. These bits are initially motionless, simply hanging in space without interacting with anything. However, gravity, the ever-present force, begins to pull them together, gradually reducing the space between them. As they come closer and closer, their combined mass and gravity increase, compressing the space around them until an event horizon forms. This event horizon acts as a boundary, letting things in but not allowing anything to escape. Once you cross this threshold, you are on a one-way journey toward the central singularity, or so traditional physics would have you believe. Now, imagine you are inside a spaceship, venturing into the event horizon of such a black hole. As you cross the event horizon, panic sets in, and you attempt to fire your thrusters to escape. But no matter how hard you try, the black hole's gravity pulls you inexorably toward the singularity. It's as if you were trapped in a corridor with no exit, being carried forward by a moving walkway that propels you at the speed of light. No matter which way you turn, you cannot escape the singularity. Known as a Schwarzschild black hole. Real black holes in the universe are far more complex. Most black holes are formed from the collapse of rotating stars. As the star collapses, its rotation is conserved, leading to the formation of a spinning black hole. These spinning black holes, known as Kerr black holes, are far more complex than their non-rotating counterparts. The rotation of a Kerr black hole adds a new layer of complexity to its structure. Instead of having a single event horizon, a Kerr black hole has two distinct horizons, an outer event horizon and an inner horizon. These horizons are like invisible walls that mark the regions where the gravitational pull becomes too strong for even light to escape. But that's not all. Kerr black holes also have regions known as ergospheres, swirling zones of spacetime where the black hole's rotation drags spacetime along with it. Inside the ergosphere, spacetime itself is twisted and dragged around the black hole, moving faster than the speed of light. If you were to enter the ergosphere, you would be unable to remain stationary, no matter how hard you tried. The ergosphere is like a cosmic whirlpool, pulling everything in its vicinity along with it. The presence of the ergosphere leads to some fascinating consequences. Objects that enter the ergosphere can gain energy from the black hole's rotation and potentially escape with more energy than they had when they entered. This process, known as the Penrose process, suggests that Kerr black holes could be a source of nearly limitless energy, if only we could figure out how to harness it. But the most mind-bending aspect of Kerr black holes is what happens inside the event horizon. Unlike Schwarzschild black holes, Kerr black holes do not have a point-like singularity. Instead, their singularity is ring-shaped, a consequence of the black hole's rotation. This ring singularity is a region of intense gravitational fields, but it does not compress matter to an infinite density as a point singularity would. To visualize what happens inside a Kerr black hole, imagine a drop of paint falling onto a piece of paper. If the paper is stationary, the paint forms a single dot. But if you spin the paper as the drop falls, the paint spreads out, creating a ring-like shape. Similarly, the rotation of a Kerr black hole causes the singularity to spread out into a ring. As matter falls into a Kerr black hole, its path is not straightforward. Instead of being pulled directly toward the singularity, the matter follows a complex, swirling trajectory, influenced by the black hole's rotation. The path of matter inside a Kerr black hole is like that of a leaf caught in a strong wind, swirling around in all directions before eventually settling into a stable orbit around the ring singularity. But here's where things get truly mind-boggling. Past the event horizon of a Kerr black hole, the intense centrifugal forces create a region of spacetime that is almost normal, where objects can move freely without being crushed by gravity. This region, known as the Cauchy horizon, is a place where the rules of spacetime as we know them are distorted. Objects and light that enter this region could potentially move around the ring singularity, avoiding the fate of being crushed to infinite density. But what does this mean for the concept of singularities? If Kerr black holes do not have true singularities, it suggests that our understanding of black holes is incomplete. The singularity might not be a point of infinite density after all. Instead, it could be a region where the laws of physics as we know them break down, requiring a new theory of quantum gravity to fully explain what happens inside a black hole. The idea that nothing can escape a black hole has been challenged by the late physicist Stephen Hawking, who proposed the concept of Hawking radiation. According to this theory, black holes are not entirely black, they emit a faint radiation due to quantum effects near